Nonlinear Regression Functions, Chapter 8, Introduction to Econometrics, Stock and Watson. Everything which we have discussed so far was linear in X. Today we are going to talk about nonlinearity in X variables, but we are not talking about nonlinearity in parameters. So in a way these models are still linear, but they are non-linear in variables, which means that their interpretation will be different than linear models. Otherwise, standard statistical inference, testing of hypothesis, everything will remain same. So nonlinear regression functions, we'll have some general comments. We'll discuss what are linear log models, log linear models, elasticities, slopes, interpretation, interaction of variables, dummy interaction, dummy continuous interaction, dummy continuous variable interaction, and at the end of this video we'll discuss 7 models, which one to choose and why. For that we need to consider, we always love to have single recipe in every application, but data analysis is simply you see this is an art, science, and many other things. Use your head wisely, think hard, because if you don't think hard, then just the mechanical recipe will not give you right results. Many models, so nothing wrong for a bit wildered which to use, decision making, exercise judgments. By looking at data, think of a reason based on economic theory or expert judgment. Ask questions. For if you have a precise question, you can have a precise answer. So that we'll discuss on the basis of those 7 models, which we'll see at the end of the lecture, at the end of this video. This what we have seen: student teacher ratio, test score. There seems a linear regression, that increase in student teacher ratio at any stage will lead to same change in test score. And now if we look at district income and test score, in district income and test score, what do we notice here? That relationship seems non-linear, because here your most of the points are below this regression line, most of the points are above regression line, below regression line. So if you think visually, it may be the case that this type of regression may be line may be better. So this relationship seems non-linear. Change in income from 10 to 20 $1,000 will not have the same change in test score as change in income from $40,000 to $50,000. So in non-linear regression functions, in variable, when non-linearity is in variables, your standard inference of linear models is not valid. That's what we are going to discuss here. So effect of a change in x depends on the value of x. That is, marginal effect of x is not constant at all places. In linear model, what do we say? Marginal effect change in x here is the same as change in y, change in x here, same y. But this marginal effect will change in nonlinear models depending upon at which range of x we are talking about. So all the 4 assumptions which we have discussed in multiple linear regression video, those remain same. Okay. That is what do we see, that what is change in x and will have an impact on y. So in linear model we monitor it we give a standard interpretation. In non-linear model it will depend at which range of x we are talking about. I am going to discuss it in a short while. You have 2 ways to capture nonlinearity in variables. One is polynomial in x. Fortunately, cubic, we don't need to go more than cubic models in social sciences, economics. So high degree polynomials are not usually required. Logarithmic function, though, you have log of x or log of y, or both log of x and log of y. Why we take log of x, log of or log of y, we'll discuss shortly. This is polynomial degree of degree r, and you have all standard OLS, standard inference. Only the difference is that your coefficient interpretation will be different. Look at this income and test score relationship. We have test score income squared, test score, income square, income cube. No, whether we to fit a linear model to a quadratic model or cubic model, that we'll also evaluate. So this is data which I'll upload after this video, that how to do this nonlinear regression in Stata, and in R I'll also provide the link of R codes as well. So now if we estimate quadratic model, this is 3.85 income minus 0.0423 income square. Please note it down. Many students confuse that there is perfect multicollinearity between income and income square. There is no case of multicollinearity here, because we are not saying effect of income holding the effect of income square constant, or income square holding the effect of income constant. This is the same variable, so both variables change. No, you have linear model, you have non-linear model. In linear model, this term is not there. So what do we say? That $1,000 income change leads to so many 3.85 times 1,000 change in test score. But here you will have income square, and when we calculate this, that if your income increase from $5,000 to $6,000, so here you have 6 square, 5 square, 5, and you see change in test score, and this comes out to be 3.4. But when income changes from 25,000 to 26,000, change in test score is 1.7, it's not 3.4. And when income changes from 45,000 to 46,000, in general, you cannot have any improvement in test score, and that appeals to common sense as well. Otherwise, recipe for increase in test score will be to increase income. Okay, one more thing, that what is test score of children having parents' income to 65,000 to 66,000 dollars. Please don't comment, because that is out of your sample range. So don't extrapolate very far into the future or backward. That's why we also not interpret the intercept, because we don't have people who have income 0. So therefore we don't interpret what is test score when income is 0. So don't interpret beyond your data's range. So this is your quadratic model, cubic model, and now we see whether income square, income cube is jointly equal to 0, beta 2, beta 3 equal to 0 or not. So it's rejected. You have this restricted model, unrestricted model, where you have these two equal to 0, that is your restricted model. The other one where you have this last one, this is your unrestricted model. And what do we see? That null hypothesis, that these restrictions equal to 0 is rejected. So it means linear is not a preferable choice. We should have either income quadratic or cubic, and so the rest of the things as it is TF, standard inference confidence interval. Okay, now we come to log. Why do we take log of a variable? Usually log of a variable may make data, non-normal data normal, non-linear data linear, heteroscedastic data homoscedastic, additive in time series, multiplicative time series components as additive. You can see from the appendix of Stock and Watson book that change in this one is the same as percentage growth rate. That is growth rate. So when you take log of GDP minus log of GDP in the last quarter or last year, so this is basically growth rate, and you can either measure it change in YT minus 1 divided by YT, or you do it like this way. So therefore when you take log and then you take the difference, that is growth rate. It's very close approximation. Now you have three situations. One is linear log model. What is its interpretation? We'll see shortly. Another is log linear model, where you take log of y and x is not taken. B, please give me attention for a second. Never compare these two models or the first model and the third model, because your dependent variable nature is different. In first case you have y. Never compare r squares of these models. Never compare r squares of these models or adjusted r squares of these models, because in this total sum of squares TSS will be different because it is in y. Here you have TSS different because it is in log of y. So therefore you should not compare r square if your dependent variable is not in same units or in at same scale. Here this one is your log, and this is called elasticity. So first case, change in this one, change in y due to percentage change in x. That is what is interpretation. Due to percentage change in x. What do we say? That if there is 1% change in x, there will be 0.01 beta 1 change in y. That's how do we interpret. And similarly, for example, here what do we say? That if income increase by 1%, the test score will improve by 0.36 points. So you see, when you have taken the log of income, to cubic model and log of income are very close approximates. So therefore, taking log of x has basically made has same results, similar results as cubic regression model. But interpretation of log model is more is easier than your cubic regression models. So therefore, log transformation is quite handy most of the times. The other one is you take log of y, and then you change your interpretation is the change in one unit or change in certain units of x leads to percentage change in y. And what do we say? That if you have a change in x by 1 unit, there is an associated of 100 beta 1% change in y. The last one that we are very familiar with, this log of y, log of x. This is basically percentage change in x leads to percentage change in y. This is called elasticity. And if we don't have this y, x, that's the change in y over change in x is slow. But when you take it in percentages form, both denominator, numerator, it is elasticity. So 1% change is associated with beta 1% change in y. This is what we have interpreted already. This is another case when you say that 1% change or 10% change in income leads to 0.554% change in x. Please do these calculations at your own. I am not doing it to keep video short. Log linear, linear log, log regression. So you see, this is basically linear model. I think this is linear regression and this is log. No, which one to use, that we'll see at the end of this video. 7 models. So summary, we have already discussed all that. Okay, we are not doing this non-linearity in parameters here. That is negative binomial distribution and all that. That is not in our scope at the moment. Okay, one more. That's very important thing. Interaction between dependent variables. Why do we need interactions? Why do we need interactions? That's the first question. For example, if I want to study what is the impact of gender and what is the impact of college degree, so gender effect will be measured by D2, college degree effect will be measured by D1, but I want to measure if person is female and having college degree, person is male and having college degree, person is female with high school, person is male with high school. That cannot be captured through this equation, because when we say that this is your college degree, its impact of college degree holding the effect of this constant, it means we have eliminated partial or netted out this effect. So therefore, both in college degree, both male and female are included. So that's why we need to do an interaction in an interaction term. Here, what do we say? That if person is having college degree 1, male 1, so 1 into 1, beta 3. This one 1, so this will be beta 1 plus beta 2 plus beta 3 plus when you have female, this will be 0, and you will have beta naught plus beta 1. This will also be 0. When you have a high school, this will be 0. So you will have this one 0. When male is 1, so beta naught plus beta 2. So that's how you can capture the effect of you see one variable along with another variable. That is in our case, that is if your student teacher ratio, that okay, before I go to that, look here, if D1 is 0, D2 is, so this is the case. If D1 is 1, this is the case. No, if D1 is 0, beta 1, beta 2, D2, and if D1, D2, when D2 is 1, so that's how you can do. I am going to explain it in here in the next video. What do we say? That you have to high student ratio and high English learner percentage. No, we have interaction. This is a dummy variable, this is a dummy variable, this is interaction of the two. No, when we say that we have effect of high student teacher ratio when there are low English percentage learners, that is, it means low English learner percentage learners, it means this term is 0. This will make whole equal to 0. So this is 0. So we are left with minus 1.9. When percentage English learner high student is 1, it means this is 1, this is 1. So your slope will be minus 1.9 and minus 3.5. So you will have change in test score, improvement in test score of will be minus 5.4, and you can test it as per these tests. If you have one continuous and one dummy variable, what will happen? That if you when D is 0, that is low student teacher ratio, percentage English learners, this will be 0. So when you will have D1, it will be beta 2 plus beta 3x. So your slope will be beta 2 plus beta 3x. So in this case, intercept will remain same, but slopes will be different. In the previous case, intercepts will be different. So that's how we discuss. The third case is when both are continuous. So in this case, you will have different intercepts. And in this case, you have different intercepts, different slopes. And slope is, intercept is same, slopes are different. So you have these three cases. Here, what do we see? Okay, you can go through these slides. I'm not covering it to keep it short. The last one which I am going to discuss is, if both variables are continuous, it's difficult to interpret, because in this case you have to interpret it at points of x. That when x1 is 20, x2 is 21, x1 is 24, x2 is 25. So you have to interpret it at different values of x. But anyhow, you can take different intervals and you can interpret it. In this case, what will happen? Your intercept will be same, your slopes will be different, and you can work it out. I may have narrated some you see might have said that slopes and intercepts different for slightly in a different way. So please do it at your own, and be with me, because I am going to present these empirical results. That's at the end of the video. That's very important to understand. Okay, this is how you can interpret, that is change in test score and change in percentage English learners, and confidence at 0%, at 20%, when here you have you are taking different values of percentage English learner, because we are assuming both are continuous. Confidence testing of hypothesis is similar. We'll discuss it in our 7 models, but please note it down. If interaction variable is significant, even these two are not significant, you should not drop these two variables from the model, because if their interaction is significant, these are called main effects. So main effects should be there if interaction is significant. Let's come to our application: student-teacher ratio, California school data. We are exploring 3 questions. Are there nonlinear effect of class size reduction and test score? Are there nonlinear interactions between percentage English learners and student-teacher ratio? So we have these variables: percentage English learner, income, lunch percentage. See whether adding nonlinear terms make our results different than what we have discussed in chapter 4, and moreover, does it make economic sense besides statistical significance? Estimate linear and nonlinear functions of student-teacher ratio with percentage English learners, their squares, their interaction terms. We'll see all these variations in our model. So our first question is different effects for different student-teacher ratio. Second is interaction between percentage learners and student-teacher ratio. Is test student-teacher ratio along with low percentage English learners or high percentage English learners will have some impact on test score? And finally, what is good base specification? For that, I have already mentioned few points. I'll mention again. Let's come to these 7 models. Look at these models carefully. So in model 1, we have student-teacher ratio significant, percentage English learners, percentage eligible for subsidized lunch, that is income proxy. All are significant. Okay, this is a linear model. Let's say it's our base model. No. Second model, again, minus 0.73 percentage English learners, percentage English learner, average district income. No, we have taken both measures of income, included both measures of income. It's again linear in variables. Model 3, minus 0.97 not significant, 5.64 percentage English learners not significant, interaction minus 1.28, high student-teacher ratio into high English learners into student-teacher ratio. But please, a caution, warning, don't throw variables from the model on the basis of their individual significance. Test the joint significance of all these 3. If these are jointly non-significant, yes, they are not playing any role, but probably they are jointly significant. So here, model 3 is, we have introduced non-linearity in variables. Model 4, we have the same up to this model 3, but we have also included this one. Again, same goes as like model 3. Model 5, we have included student-teacher ratio cube, so interpretation will become difficult. All these 3 will be interpreted together. Percentage English learners, income. So everything seems significant, and what do we see? That there is impact of the impact of these variables. If we don't include these variables, this will lead to omitted variable biases. let's go to model 6. The difference between model 6 is that we have not only included student teacher ratio and student teacher ratio cube, we have included interaction, their interactions with percentage English learners. Oh, that is basically leading towards non-linearity and cubic models and all that, and it's making it really tough to interpret. And these variables. In the final model 7, we have 11 point, these variables which are significant only we have in model 5 and model 7. The only difference is that we have here included percentage English learners, and here we have not included percentage English learners. So these two, we'll see these cubic models and we'll see what's the difference between 5 and 7. Okay, that's it. Now you see, to find out which model is appropriate, as I mentioned, that you have to think logically, you have to use your head, you have to think in terms of economic theory, expert judgment, you have to ask the right questions, you have to be precise in your questions, and then you can find out some answers rather than blindly following that, okay, r bar square is this one, this one, this one, so we have highest r bar square here, so therefore this one is the best model. No, that should not be the case. So from this, what was our question 1? That whether holding percentage English learners impact on student teacher ratio fixed, can we what's the impact on test score? So we want to we see that this is your cubic model, and this cubic model indicate that there is a slight difference as these variables are significant. So including high English learners will have an impact on test score. We'll also see with the help of a diagram. Second question was, after controlling for economic background, there is evidence of a non-linear effect on test scores of the student-teacher ratio. And this effect is statistically significant, as well as the student-teacher ratio square and student-teacher ratio cube are also significant. So after controlling income, we have student-teacher ratio square and student-teacher ratio cube effects are significant, which indicates there is non-linear effect. Okay, now if you look at cubic regression 6, 5, 7 and linear regression 2, so you see there is some sort of non-linearities and slight differences in change in test score at different levels of student-teacher ratio. So superintendent's problem that reducing class, he wants to reduce class size by 2. Okay. In general, it will not have different impact at different ranges, except at the very beginning or at the very end, where very few data observations lie. And if you look at this model 6 and cubic, this one is cubic. Let me see. So you see, we have more or less similar slopes. Other than this range, below this one and slightly at this, your slopes are more or less same. So therefore, what do we say? That English learner will have not much impact for most of data range. That is controlling English percentage learners in classes will not have much impact because your slope of the equations remain more or less same. So that's what we have discussed so far, and probably we have completed our first question, whether class size reduction leads to improvement in test score. We have discussed simple linear regression model, they're testing heteroscedasticity, homoscedasticity, why robust standard errors, Gauss-Markov theorem, why Gauss-Markov theorem has limited applicability, what is omitted variable bias, what are the conditions for omitted variable bias, how to do joint testing for the coefficients, F-test, okay, and then we have covered nonlinear